This presentation presents cognitive load theory and the application of schemas. It illustrates how to appropriately design instruction to minimize a learner's cognitive load and maximize instructional efficiency to optimize learning. The cognitive load can be described as the mental load or mental effort of the learner, both of which affect performance. So as you can see here, as our mental effort increases, this places more strain on our cognitive load. Sweller described the cognitive load as a construct representing the load that performing a particular task imposes on the cognitive system. The cognitive system, or cognitive architecture, is made up of the limited working memory and the long-term memory. The cognitive load directly relates to the working memory load. The capacity of the working memory was illustrated by Miller to hold about 7 items at a time. More recently, however, the working memory has been described as having a capacity of only 4 items being held at a time, whereas the long-term memory, where schemas are held, is unlimited in its storage capacity. The cognitive load is made up of an intrinsic and extrinsic load and is dependent on the interactivity between elements of information. I'll explain the intrinsic and extrinsic cognitive load shortly. But firstly, what is element interactivity? So there can be a low level and a high level of element interactivity. A lower level requires a lower level of cognitive load and is easier to understand, whereas a high level requires a higher level of cognitive load and is harder to understand. In low element interactivity, information is presented in a serial manner and doesn't interact, whereas in high element interactivity, elements are learnt simultaneously and are interacting. Low element interactivity is subsequently better for novice learners, and high element interactivity is better for expert learners. The element interactivity relates to the intrinsic and extrinsic cognitive load. The intrinsic cognitive load is necessary for learning because it is intrinsic to the material being dealt with. It's also dependent on instructional goals and prior knowledge, whereas the extraneous or extrinsic cognitive load is the unnecessary cognitive load that can be altered by instructional interventions. For example, if I was to try and describe a square to you, to describe it verbally would take an unnecessary amount of time and may involve a high level of element interactivity, placing an unnecessary strain on the cognitive load. Whereas if I was to show you a visual image of a square, it would take just a few seconds and involve a low level of element interactivity. So the cognitive load is made up of the intrinsic and extrinsic load. You can see here cognitive load equals intrinsic plus extrinsic load. Ideally, the intrinsic productive load takes up more of the cognitive load than the extrinsic unnecessary load. But unfortunately, if the instructional design is poor, the extrinsic load may take up more of the cognitive load. So you can see here, the extrinsic load is taking up a lot of the learner's cognitive load, which is not ideal. It may take up all of the cognitive load, and the two might take up a greater amount of the cognitive load than is possible, causing cognitive overload. This may be due to learners not having the required schemas necessary for learning, which I'll discuss more about shortly. They may also not take up enough space, meaning the material may be too easy for learners. So ideally, you want to maximize the intrinsic cognitive load, the productive load for learning, and minimize the extrinsic wasteful cognitive load. You may do this through a number of ways, such as the application of schemas. By utilizing the interactivity between elements of information and understanding students' level of prior knowledge, you may facilitate the activation and development of schemas. So what are schemas? Schema theory illustrates that knowledge is stored in the long-term memory in the form of schemas. Schemas organize and prioritize information based on previously learned knowledge. This organization reduces the working memory load by a process of automation. For example, children learning single-digit addition may need to use their fingers to keep track of their calculations in order to free up space in their working memory load. With the extensive practice, however, this process becomes automated and the working memory load is reduced. Schemas relate to long-term memory, working memory, and sensory memory. The held in long-term memory affect what is in working memory and what is in the sensory memory. So how does cognitive load relate to schemas? When learners find the material too difficult to learn, they may not have the appropriate schemas, which may overload their working memory. Learners who have a more automated schema have more working memory capacity available to use the schema to solve more sophisticated problems. So how can you design instructions to activate and develop learners' schemas? Understand the student's level of prior knowledge. This may be done by simply asking questions if they've learnt some material before, or could be done by using a pretest before teaching material. So you are activating relevant prior knowledge to link with new information by priming appropriate schemas to build on top of a learner's existing knowledge. You may also chunk information to help learners organize their knowledge into meaningful groups. So let's look at an example. When learning two-digit addition, schema automation and working memory are two salient factors. So when teaching two-digit addition, you may ask students if they have learnt single-digit addition and if they know how to add groups of 10. If so, these may already be stored in their long-term memory and they will find it easier to learn a two-digit addition strategy, such as the split strategy. If students don't have these schemas, they'll need to rely on their working memory, placing a greater demand on their cognitive load. So this example uses a worked example first. A worked example consists of a problem statement followed by the solution steps, including the final answer. This may help students activate their schemas and also show them the appropriate steps to solving a two-digit addition problem. A worked example such as this will reduce their cognitive load as they don't need to search for the correct strategy and can instead focus on the steps involved in solving the problem. Therefore, if the appropriate steps are taught initially, students are able to decrease the number of steps involved, free up space in their working memory, and generate a higher mental calculation efficiency. This process reduces the number of elements of information that a learner needs to process, making them more likely to develop the appropriate schemas. So how else can you facilitate the development of schemas? Consistent practice, such as using Minute Math worksheets, may be used. This processes will begin to occur as expertise develops. Extensive practice creates these automated schemas that allows fluid performance of mental calculations. This will free up space in their working memory, allowing for processing of unfamiliar aspects of tasks that would otherwise be impossible. So our cognitive load is limited by our cognitive architecture, which is made up of the limited working memory and the long-term memory. The long-term memory is unlimited and it is where schemas are held. Therefore, developing schemas should be the goal of learning. Acquiring expertise in a subject and creating automated processes, freeing up space in working memory for efficient, effortless mental processing and problem solving.